Okay, hello everyone. Starting a little late here. We were talking about talking about multi-computation and building applications of it in Wolfram language. And let's see, last time we had finished by talking about, well, we were talking a little bit about functions that manipulate pure functions. And we actually, in a different meeting, we're talking about functions that manipulate held expressions, and maybe we should hold those thoughts for that other meeting. We'd also been talking in this meeting again about another topic that arguably should be in other meetings, which is about this concept of, well, we don't have a great name for it yet, aware supply, this thing that can pull in ambient information when a function is applied in a particular environment. Now, I think the bigger picture here, and maybe if Nick is here, he might have something to say about this, is the kind of the representation of evaluation. In other words, what we have mostly concentrated on in our language is you have an input, you compute, you get an output. The question is to represent the process of computation. How do we symbolicize the representation of the process of computation? And trace was an inadequate answer to that from 1990 or so. And we are now interested in, how can we go further? So I don't know if is Nick with us? If he is, maybe he has something to say about this.
Oh, not much. Not really. I just have some ideas about maybe generalizing token and graphs, how you can make it more multi-computational and so on, but not really something concrete.
Okay. Well, I mean, I think the issue with trace is kind of gives you a sequential history. I mean, the way I view it right now is, trace is giving you a sequential history of a computation. There are these two different aspects of how you get to the next part of the computation. One is reevaluation, and the other is recursion through an expression. And that's sort of one thing. One point about trace is that trace is clearly giving you only one computation path. If you had, for example, pattern matching, and there are multiple, matches that could happen, trace is only going to show you the result of taking one of those matches. And what we ultimately want is a multi-way graph that represents all possible such matches, because then we think that we're going to be able to do sort of other types of computations where we're tracking not just the one match that happened, but all possible matches. But I think what we've got we have this continuing challenge to, on the one hand, we can have something where the states of the system are well represented, but where there is redundancy when it comes to looking at different branches of history, or we can have something like a token event graph where we've shattered the states so that we don't have redundancy across different branches of history, and we're only showing separately things which are genuinely different, but then it's unclear how to reconstruct the states. And we were talking last time about Jonathan's Glocal multi-way systems as a way to go between those things. But I mean, that's kind of the and now, I mean, I guess we had also been talking about another thing that had come up was the question of lightweight, if we're actually going to implement multi-computation, doing lightweight parallelism within, for example, within the evaluator. And I think Christopher had mentioned some possible ideas, and we're jumping around different topics here, but Christopher had mentioned some possible ideas about how to actually implement lightweight parallelism. Is there, I mean, and I don't know.
Well, I don't really have any ideas. I mean, I have no idea how it would work. And I mean, I don't think yeah, I mean, I'm not sure. I'm not sure how impossible it is anyway, but yeah.
Okay. All right. Well, so we have, and then, okay, maybe we should make a list of what are the related things that we are trying to work on. Okay, just to this is our list of targets, so to speak. So we have, let me just save this away in the right place. You know, finally, I have been for many years, I've had this naming convention for files where I start 01, etc. And finally, with this metamathematics project, I finally hit 100 with the number of files in a given topic. Okay, I'm not sure that's a good sign or whatever. Okay, so let's just make a little bit of a list of what we think we're doing. So one thing is sort of the generalized trace. Well, okay, one thing is situationally aware function application. And that's another thing is generalized trace symbolic representation of computation. Oh, look at this. Ian is putting something in the chat. Hold on. Let me just generalize trace symbolic. Okay, so another thing we've been talking about is, which again I think is not quite so related, is manipulation of meta-programming manipulation of held expressions. Once we have this, okay, so then we've got sort of the multi-way generalization of evaluation, which turns into kind of things like multi-replace. Let's see, another thing that we have been starting to talk about was manipulation of function objects. We just started talking about that last time. And we also talked about, yeah, okay, that's another one, manipulation of patterns. And, well, another one, well, then there's also lazy and infinite data structures. Lightweight power, there's a lot of topics here. Lightweight parallelism in the evaluator. And as soon as we have multi-way generalization of evaluation, we've also got these things about traversal. Well, I suppose that's even a separate topic. I mean, it's symbolic description of traversal orders. Yeah, that's a topic that even occurs even without multi-way computation, although it's more poignant in that case. All right, so Ian, as a piece of code, Ian, can you say what this code is supposed to do?
So this is some code that Jose and I put together of converting the output of trace into a tree.
Ah, okay. All right. Okay. So let's you know what? I'm going to put this in a separate notebook here. Okay, so let's take a look at that. So where would we have a good sample of trace output? Is this a sample of trace? Where's a good sample of trace? Do you have a good sample of trace?
You should have a function definition there.
Okay.
F of 0, F of 1.
What you mean in this other notebook?
In that notebook, yeah.
Okay. All right. Okay. Okay. What is this? This is all in one cell. Well, I don't understand what is this?
This is x equal 1 semicolon x plus plus.
Okay.
Maybe try running trace of that for comparison.
Or copy out that trace and have that as a separate input.
Okay, so let's take a look here. So x equals 1, x plus plus. And now what you're saying is, and I'm a little bit confused here because this is kind of a head. Oh
That's
gosh,
because I
what the
did
heck
trace
is going
original
on?
goes to true.
What does that mean?
You change that to false, you get the default behavior.
Okay, but so let me try doing this.
Just do nest tree of like percent there.
Of that, like this.
Mhm.
Is this helpful? Let's try to understand this first of all. Okay, x equals 1, x plus plus. Okay, x equals 1 gives 1. Okay, x plus plus evaluates x. What the heck is that 1 doing there? Is that the return value? Oh, I see. X gives 1, and then this is the return value there. Okay, let's do a more serious. I mean, let's do something. Okay, so let me just
in your notebook on the right, you have a function definition at the bottom.
Maybe you could try just like a Fibonacci, like a little recursive Fibonacci.
I will,
of
yeah.
like 3.
Okay, but so this is now a compound expression. So that's okay. There, Fibonacci, good. Let's get rid of my X definition here before it blows everything up. Okay, there's Fibonacci. And now, what do I want to do? I want to do trace of 4. So let's go ahead and say, so do I need all this apparatus here? Infinity trace data, what do I need here?
Just change the inside of the trace.
Okay.
Maybe set the aspect ratio to be really wide.
Well, I'm going to just...
So the exercise here is to distinguish the reevaluation vertically from the follow other elements horizontally. Or perhaps I'm saying it in reverse. I always have to think.
So I would have expected that you'd have the f of 3 at the top, and then a child of that would be the f of 3 minus 1 plus f of 3 minus 2. And then that would have the children.
That's what I would have expected too.
3 minus 2, you know, etc.
Compare this to what just trace gives.
Well, I mean, trace may be just completely wrongly designed. Just
well,
to
it does something systematic.
I understand.
So here,
Okay, so-
f of 3 is actually a sibling. We've made it a parent in the tree.
Right, but it should be this. Everything that comes from this is causally dependent. Look, if we think about what needs to have existed in order for something here to be done, I don't even understand. What is that 312? What the heck is that? What is that? Why is there a list? Why is there anything like a list anywhere here? I don't understand.
That is representing a sub-evaluation.
What kind of a sub-evaluation? Oh, you mean 3 minus what? But I don't understand. I thought the evaluation went down the page here. Okay, look, you've got two kinds of edges. This is what we keep on talking about. You've got an evaluation edge, 2 minus 1 is 1. And here you've got a recursion edge. I'm looking at the first element of the list and the second element of the list. Is that correct? And what the heck is this f of 1 doing here? What is that? No, this is the wrong way around. I mean, Trace is doing something completely crazy, in my view. And maybe
Might
Trace
make more sense if you did trace original goes to true.
Okay, that does potentially make more sense. Okay, let's take a look at this creature. All right, f of 3. Now, its child nodes. Oh, I don't understand this at all.
So the standard evaluation procedure for an expression is to evaluate the head.
I know.
Then evaluate the arguments. That's what you see. So there's a child for f. There's a child for 3. But then the child for f of 3 evaluates and becomes f of 3 minus 1 plus f of 3 minus 2.
But why isn't that an arc going, an edge going down?
Because it's not evaluating a sub-expression. F of 3 gets replaced with f of 3 minus 1 plus f of 3 minus 2.
I know, but
edges going down when you're evaluating sub-expressions.
What? Why is f of 2 minus 1 a sub-expression of f of 3 minus 1? No, this doesn't make any sense. Look, the sub-expressions of f of 3 are f and 3. Right, and those are fine. I mean, so we really want two kinds of edges here. We want a sub-expression evaluation edge, and we want an evaluation edge. And we want a sub-expression recursion edge. Okay, claim. We need a sub-expression recursion edge. And we need a replacement substitution reevaluation edge. Mm-hmm. Okay, and
right. So this is just showing the recursion edges, and the replacement substitution reevaluation edges are not shown. Those are just siblings.
Yeah, which is completely, utterly confusing. Okay, so now my claim would be that in the simplest case, the replacement edge is just of the form, initial expr, arrow, final expr. But the full representation is more like a token event graph, in which there's another incoming edge that brings in the rule for doing the doing the replacement. Does this make any sense? So in other words, if we see here f of 3 goes to f of 2 plus f of 1, that is a mere, that will be showed up as initial expression, evaluation edge, final expression. But in reality, what we should be seeing there is something of the form, rule plus initial edge, initial goes to final. Does that make sense? And now that's the, and in the multi-computation case, it's more like rule plus initial goes to final one, final two, final three. Is this making sense to people? So I claim that's the graph we want. We want a recursion.
So I understand, I think, that you want some kind of visualization that would show a relationship between the f of 3 and the f of 3 minus 1 plus f of 3 minus 2. That includes the rule, like you're saying there.
No, but
I'm not sure what the graph is that you're wanting. Like, is it adding additional edges to the graph above, or is it some different structure?
I don't know, because I think some pieces of the graph above I absolutely do not understand. Okay, I don't understand why there's an f of 3 here when there's already an f of 3, and why that's a sibling node. It just doesn't make any sense to me. It just doesn't make any sense that this, look, what I would expect is there is, okay, so let's see if we can draw the graph that corresponds to the map. Okay, what I would call the map all graph, okay? Okay, so what does that mean? That means a graph where we have an expression. Let's say we've got, f of g of x of g of y of comma g of x comma whatever. I don't know. We add in some other things just for fun here. F of g of y whatever. Okay, so this thing, that thing has. Okay, so let's try and make the expression tree of that. I know which expression tree we want here. What the heck? Oh, for God's freaking sake. This is what we get for doing this. I hate doing that. Okay. What's the most appropriate expression tree to represent the operation of map all? Do you understand what I'm asking? You've got a version of expression tree that will show me in its nodes will show me the successive expressions that are fed to map all. Do you understand what I'm saying, Ian?
Do comma sub-expressions.
Okay, so because what I want to see is if I take this thing, why isn't this working? Okay, if I take that thing and I say map all of echo, comma this. Okay, boom, there I get that.
Yep.
Right? Okay, so now what I want to see is expression tree of that, comma, what, sub-expressions?
Yep.
Okay, I don't know what those two arcs are doing there, but, oh, I see, there we go. Okay, so now let's look at this compared to this. I don't understand this at all. So in the recursion, that would be the recursion of where slash dot, where the evaluator visits. What the evaluator makes a depth first traversal of this tree. Is that correct?
Minus attributes, I guess so.
Okay. All right, so we can see that presumably. How can we see that? I'm surprised map all doesn't show. Oh, I see, map all. Okay, what I really need to do is heads arrow true. Either that or the sub-expression should have a heads. Is there a heads false option for the sub-expressions thing?
There will be. For now, replace sub-expressions with the string arguments.
Okay, so now let me go back up here and replace that. Okay, so the claim would be that this thing here is the same as the map all results. If we do a depth first traversal of this tree, we will get the same sequence as that sequence there.
Yep.
I believe that to be correct.
Yeah, if you did a tree map of echo over the expression tree, you'll get the same echo.
Okay, all right, so let's just understand here. So if we do a map all here with heads goes to true, we'll get that. And that will correspond to this, okay? F, G, yep, okay, fine. Okay, so, and that's what we get with when we do a tree on this tree here. What you're saying is if we take that tree and we do a tree map of echo on that tree, we will get the same thing, right? Now, were we to do a tree map with a different traversal order, so let's just, to understand what we're doing here, we would say traversal order, is it tree traversal order?
Tree traversal order.
Okay, so now let's say, is there a breadth first option?
Yep.
Okay, I don't understand. Oh, I see. We got back out the same expression here, but here, breadth first, beautiful, beautiful. Okay, I understand how that works. Okay, so this kind of tree represents our essentially expression traversal. I mean, it's a little confusing that okay, so expression traversal is the depth first version of this tree. Expression evaluation, in a sense, we can connect any one of these things to another. So for example, let me just do a trivial case here. So if I do the same thing, if I do an expression tree of arguments, oh, what is happening with this multi-click? Why is multi-click not working? Who knows? Okay, so let's just do this. Let's say I've got a Fibonacci and I've gone 2 levels and I'm going to call it plus lowercase plus just because I don't want it to, actually I could do an active plus, couldn't I? If I just say f of, 5 minus 1 plus f of, let's say 4 minus 1, no, sorry, 5 minus 2, and then that whole thing plus, let's say, f of 6 minus 1 plus f of 6 minus 2, let's say, and then I want to inactivate this.
No, just wrap the whole thing in unevaluated.
Couldn't I say inactivated?
You're not going to be happy with the answer you
Okay,
get.
so can you fix that and have a version?
It's nothing to be fixed. You just don't want to see an expression tree with lots of.
I know that. I know that. I want you to make an expression tree which ignores the inactive things. Okay. Okay. Okay, beautiful. So now let's take a look at what this is. Okay, so this is the recursion. This is the pure expression traversal recursion of that object. Okay. Oh, but it evaluated. What the heck? Wait a minute. I don't understand.
I mean, tree doesn't hold the data, so
well, so maybe
held arguments instead. The string held arguments.
Okay. Okay, so this is now pure expression traversal recursion. Okay, but now what's going to happen is then there is the evaluation recursion. Am I making sense? So from this tree, we now have another edge that comes from, let's say, f of 5 minus 1. That other edge is applying the rule to get to f of, 5 minus what? Well, no, actually.
So in order to have done this first, the symbol plus would have evaluated. And then the two branches you see are the result of evaluating the arguments. And then you need a representation for applying plus to its arguments.
Yeah, but the thing I'm trying to say, yes, that's what I'm talking about.
We've now evaluated the sub-expressions according to the standard evaluation procedure. Now we want to apply a rule to what we got.
Exactly. So the question now is, let's just take 5 minus 1 here. Okay, let's take a much more trivial case. Okay, let's take 2 plus 3. Okay, we've got this. That is a representation of sub-expression recursion. Okay, now we need something else here. We need another edge coming out of this. And what's very confusing here is that, where is time in this whole thing? I mean, this is where, arguably, is there a notion of reverse graph here or reverse tree? No, how do we get this into, oh, for goodness sake, it doesn't label those. Well, okay, so let's say we have this. What is going on with multi-clicking here? Somehow multi-clicking is broken. Can somebody, I don't know what version I'm running. Let's see what version I'm running here. That's really odd and worth checking into.
Yep, I can look into that.
Okay. I don't know why it doesn't draw it upside down, but what happened here? Oh, I see, because it's got tree. Those are tree labels here, right? So if I say vertex labels arrow v underscore colon greater than first, will I get the right thing? Do you understand what I'm doing here? Did I get the graph the wrong way around again? No, I didn't.
You did a reverse.
No, I know that. But so what's happening here is 2 and 3 together make 2 plus 3, which then takes a rule from the outside world and makes 5. Does that make sense?
Yep.
And but here, one of these these edges, we can call them, structural edges or something. Okay, so one thing we could say is there would
really be another edge from the symbol plus going into that.
Yes,
well.
There would be. So can we do that with heads goes to true somewhere here?
Do held sub-expressions instead of held arguments.
But by the way, not to throw a complete wrench, but I mean, how is this supposed to deal with things like up values?
That is a wrench.
Presumably, we have to display the rule a certain way.
No, you know what that is, Christopher.
Applied a down value or applied an up value, or
yes, but
you're going to argue that it's just the same as down values because it's just a replacement.
Yes, but the point is, no, I'm not going to actually argue that completely. I'm going to say that's actually an interesting idea because it's essentially an edge that connects. So the evaluation edge would normally just say, bring in, okay, the evaluation edge, okay, here's a claim. Okay, wait a minute. There are structural edges representing how expressions are built up, are structurally built. Okay, then we've also got separately, there are evaluation edges representing actual transformations. Okay, so what's the input to the actual transformation? My argument would be here, the input is plus, because that's the thing that has the down code. Whereas if there was an up value, the input will be from further down in the tree.
I thought the input was plus of 2, 3.
No, it is.
Yeah, I
but
would have thought it'd be the whole expression.
No, I know that, but the whole point is, okay, look, the whole point is, like in a token event graph, there are 2 inputs here, okay? So let's look at how this works for, Nick, can you give us an example of something where we're applying a rule in a token event graph and we see a substitution happening?
Substitution where? It's like just applying a rule, it's already substitution.
No, I know, but what I'm trying to see is, in a token event graph, right? We're going to make help how to do this. I'm trying to see something where I'm going to have an edge. I'm going to have something that says, you know, f of x blank goes to whatever, x plus 1. And then I'm going to have, that's 1 token. And then I'm going to have f of 7. And then that's another token. And those 2 things come together in an event. And the event consists of applying this rule to this object, right? And then the result is f of 8, or is 8 or whatever, right? How do we make that again in a token event graph?
Oh, you can make like a specific pattern. For example, your rule would be, left-hand side of your rule would be like a list when the first element expects a rule, and the second element would expect some just arbitrary expression.
Right, but that's exactly what's happening when we use a substitution lemma. Or don't you have code that does that? That
No, you
takes,
can use the token event graph. You just make a rule that has left-hand side, like 2 elements in a list, right?
Can you just show me the code? I'm not understanding this, but
Okay, we can try something.
the point that I'm making is these structural edges, I claim, make a tree here. Although even that, if they're common sub-expressions, there would be a DAG. Am I making sense? But they, I mean, you know, this is mostly a tree, except for common sub-expressions, or e.g. X, which is a shared thing.
In general, like the 2 and the 3 would have been things that came from the evaluation of some other expression.
Yeah, right.
So I don't know that the arrow is really pointing from a sub-expression into it so much as it's pointing from an evaluation. Like the nodes are.
Well, no. There's 2 different things here, guys. And Jonathan sent a giant piece of code here, which we're about to try to understand. Jonathan, can you send an example of how this is used? Ah, very good. Okay, let's take a look at this. Okay, hold on. But I'm trying to explain this again. Okay, and this is something which, in fact, interestingly came up just yesterday in connection with the compiler. In the compiler, an expression is a bundle of 2 things. An expression is a structure, a struct, and it is also an evaluation semantics. You know, we have both of those things bundled together. You know, the evaluator and the things we do with expressions, both any expression is automatically acted upon by the evaluator. That is our standard model for our language. But we can imagine an expression devoid of evaluation, the thing we were calling exp_struct yesterday, and then we separately can add an evaluation. So what I'm saying here is the structural edges business is the story of an expression devoid of evaluation. Does that make sense? It's saying how is the expression put together, but that's independent of how evaluation happens. And that reflects the evaluator. Look, the evaluator, when all it's doing is echoing, the evaluator is just visiting parts of the expression. Doesn't happen to do anything with those parts of the expression. It just returns them unevaluated. But if it were to do something, there will be 2 actions that it takes. In the, you know, the operation of the evaluator comes first from its push to recurse, and second from its push to replace. right? I mean, so a way to say this is the evaluator.
And of course, when it's hold all, then it's first by its push to replace and then by its push to recurse.
Right. But so it has two fundamental operations: recurse in structure and replace a structure.
With replace taking precedence because of things like attributes.
Well, yes, that's right. But I mean, in right, and the
Depending on the
attributes
attributes,
control which happens first.
you're gonna change how you recurse or not recurse at all.
Yes. Okay. So Nick has a thing here. Let me take a look at Nick's, and then we'll look at Jonathan's. Oh my God. So complicated already. Okay, let's try to understand this. Okay, f of 3. Oh, I see. F of 3 uses the rule, this rule, to produce f of 2 and f of 1. Is this making sense to people? These are evaluation edges. Yes?
The f of 3 and the rule node, are those supposed to be graphically distinct things, or are they supposed
Yeah,
to
those are that rule node is a different color for now. I mean, in the end, it's just an expression, right? But for now, we're thinking of that as that is a rule to be applied. If that was down code, internal code in the system, there will be no visible node here. It would merely be a magic pixie dust that is used in this actual evaluation, event to produce f of 2.
Mm-hmm. So do the yellow disks always have exactly two parents, an expression and a rule?
Yes, in this case, yes. They're saying an expression and then what you do, and then a rule that describes what to do to that expression.
And it has two children because...
No, it doesn't necessarily have two children. In this particular...
Well, I'm saying it has two children because of the right-hand side of this rule.
Yeah, I mean, yes, because Nick is representing lists as a multi-computational kind of thing. I mean, I would say that normally this would have one child, and that's where we get this relationship between the recursion, the pure structural recursion, right? Normally this would have one child.
Yeah, the one child would be like f of n minus 1 plus f of n minus 2.
Exactly. So, I mean, I'm sure we can just change Nick's code here. Can we, Nick? And just change that to f of n minus 1 plus f of n minus 2 here. And then it probably won't do anything very exciting. It'll just show, okay, it's got some weirdness in there, but basically that's showing this phenomenon, right?
Yep.
That's just showing f of 3 goes to this. And then what we...
What's the other arrow going from the disk back to the rule?
I don't know.
Trying to reproduce it. It's also an output. Because a token on graph by default removes the token that comes into event. And in order to keep it alive, so to speak, you have to reproduce it.
Right. So what Nick is saying is if this rule is an external force acting on the system, then it has to be, gosh, that's an interesting way to think about it. That's like an external potential in physics that outside of the system and always there. But Nick is saying if you want to go microscopic with it, then it has to be the case that the event, gives you back that rule. Otherwise, the rule would have disappeared. Otherwise, we've erased the code, basically.
So there's two kinds of incoming edges and two kinds of outgoing edges. Like edges to and from expressions and to and from rules.
Well, look, okay. Like in this metamathematics project we've been doing, those two rules and expressions merge in the end. But at this level, we're treating them as distinct. And certainly with respect to our internal code, that's a rule that you cannot look inside, so to speak. Right, that's a rule that's an atomic rule, so to speak. Atomic conserved rule, right? E.g., rules that persist are like external potentials in physics. And e.g., down code persists. And it doesn't need to be, I mean, again, in Nick's description of a token event graph, one is going full microscopic and one is having to say, let us actually say that that rule is preserved by explicitly having it come out. Okay, should we look at Jonathan's thing here? Okay. Okay, what is this doing? Jonathan.
Well, I was asking a question, which is what we want a glocalized version of this?
I don't know. Can you define terms?
Sure. I mean, obviously, this is just the multi-way. This is the multi-way state evaluation semantics for f of 5, given the Fibonacci rule. Given
except that it's done something here. It's done essentially a breadth first compression, right? But this is not, in fact, the evaluation semantics of our current evaluator. Right, the evaluation semantics of our current evaluator is a pure tree with no sub-expression combination.
Well, so each sub-expression is being simplified only to the extent that the front end automatically simplifies it.
I understand, but I'm saying that
I don't understand the edge from f of 3 plus f of 4 to f of 4 plus 3.
So f of 3 is being evaluated to 3.
Yes.
Do we see that?
But normally, okay, Ian, can your code generate the standard Fibonacci evaluation tree?
Yeah.
Okay, how do we do that? We do that with trace with a, where is it?
We did it already, didn't we?
I mean, if you want the thing with no sub-expression reevaluation, you just run the multi-way operator system like that.
Okay, let's try it.
Sorry, that's for f of 4, but you can change it to f of 5 for consistency.
Does anybody have any idea why the graph drawing system puts that node there? I think, Avery, if you could just point this out to Charles. I just don't think it makes any sense. I don't know why it does that.
Yep,
why it
I can
folds
do
it
that.
under like that.
Mm-hmm.
Okay, in any case.
I think this is still being smart to an extent.
Yeah, it is a little bit, but only in the rendering.
Yeah, it's getting rid of parentheses in the rendering, I think.
But the actual underlying evaluation is as dumb as it possibly can be.
No, wait a second though. Wait a second. This is something where every node will have the same value. Will have the value of f of 4, but that's not the same way round. Oh gosh, I'm confused here. That's not the same way round as what we would get.
You're like doing the replacements in place, right?
Yes, in this case.
And showing how it evolves.
Right. So normally, what I would expect is let's see, can we get Nick's system to actually show us? Okay, we got f of 3. No, it's not going to show us this either. But in principle, okay, if we had another node here, if we had another event that was the down code for plus, then Nick's system, in fact, why don't we just do that? Why don't we have something here that, can we do that? What can we turn this into? Here we can go. Let's try doing this. Okay, instead of this, let's call it P of that, comma that. Let's have another rule. Wait a second. Why? Nick, can we have another rule here that is also applied that says P of? Okay,
yeah,
so how we do
just a list of tokens. You just add another rule.
Okay,
and
so
you have
P of
like,
A blank, B blank. arrow a plus b.
Do you want to say blank integer?
Maybe I do.
Just to simulate that the plus wouldn't
Yeah.
be doing anything until the things had evaluated.
Can you remove the splice? Don't need it.
Where even is the splice? I don't even see it. Where is it? Oh, there.
Yeah.
Okay, do I want to, let's see, that 2 probably wants to increase. Oh my God, these things are hard to understand. Okay, so what's happening here is f of 3 combined with that rule turns into p of f of 2, f of 1. Okay, I think we want the end conditions as well, don't we? In order to make this sensible. Do we want, so let's give the end condition f of 1, arrow 1, f of 2, arrow 1. Oh my gosh. Look at this creature.
It would look better if we like remove those extra cycles. That's what we do for the mathematics case.
Okay, how do we do that?
But I have like a separate function for that.
Can you send it to me?
Yeah.
Okay, the thing that's bothering me is that I'm not seeing a 5 or something come out here. I don't understand why I wouldn't be seeing that. Why am I not seeing the application of the P rule actually giving results?
Because it's not an integer, right? The only P expression you have with F's inside.
But I have to hit the base case to get an integer, is what you're saying.
Yeah, it's not drilling down the expression, it just applies to the whole.
But wait a second, but I see. So this doesn't have the recursion part of the evaluator, is what you're saying. This is only whole expression, and that's perhaps where Jonathan's glocalization comment comes from. Is that right, Jonathan?
Well, this is what I'm asking, right? I want to make sure that I understand the problem.
Yeah, I think that is a statement of the problem. That is we have in the end here. Okay, we've got a multi-way graph, which in the case of our particular evaluator, resolves to a single-way graph that represents the evaluation. But then the question is, what we want to do is to represent not just because the operations are not just being done on whole states, they're being done on these sub trees. Yes, that's essentially what we're talking about, is this interplay between whole state reevaluation and recursion into an expression, which I think is the same as the glocalization problem. Is it?
Well, I think so too. That's what I was confirming. I mean, actually, if you let me share screen for a second, I can show you.
Yep.
So the full operator form, I showed the combinator version. The full operator form of global multi-way system is not yet in the function repository, although the code is complete. But that would be this would be the global version of that evaluation.
Okay, let's take a look at this puppy. F of 4.
Right. So we start with f of 4. We evaluate to plus f of 2, f of 3. So we've got two versions of the f token, one version of the plus token, one version of the 2 token, and one version of the 3 token.
But wait a minute, those have been deduplicated. So the f token, this is like our symbol table. It's at least at this time, this evaluation slice, it's been deduplicated. There's only one f here. Even though,
but there are two edges to it, crucially, right? So
Yeah,
you can
right,
tell
I
this,
see that.
this event is generating two Fs.
but how do we
F2
know that it's
versions.
how do we know that the expression being represented there is plus of f of 2, et cetera, et cetera, et cetera, rather than just a bucket with a plus 2 f's, a 2 and a 3?
Right, exactly. So each of these edges is tagged with essentially part specifications of where these things lie in the expression tree.
Yes.
I still need to figure out a better. So obviously, for the pure, graph rewriting case or something, that doesn't matter because the way that you set up, the way that you order hyper, there's no kind of hierarchy in the way that you order hyper edges. But for general expressions, there obviously is. So I still need to figure out a nice way to visualize how that edge tagging information is actually stored.
Well, you are flowing right back into the same question that we keep on having, which is these two forms of essentially graph. You are representing an evaluation graph here, and as you say, you have to superimpose on that this expression graph, structure graph, and also, in our usual physics project hyperedges thing, all we've got is flat ordered lists, effectively, of atoms. But in this case, we have more structure to that. We have whole expressions rather than just lists of atoms.
Right.
And
so
yes,
my initial thought, although this might end up being completely incomprehensible, is that right now we have two versions of edges, right? We have the causal edges between the rewrites, and we have the evolution edges between the tokens. My initial idea was to superimpose a third kind of edge that showed essentially the parent-child relationships between elements of the expression tree.
Yeah, I agree. Yeah, I think that's the thing to try doing. And that was what I was asking Ian for before. That is, Ian has gone from, and you probably use Ian's technology for this. Ian has the tree, basically, as a tree, right, that represents, and what I was asking Ian to do was to add the edges that you have here that represent evaluation.
So this is actually touching on one of the key differences between a tree and a graph, which is in graph, it's kind of like just a bucket of vertices and edges.
Mm-hmm.
There may be some inherent ordering, but in tree, there's like these siblings. You are ordered amongst your siblings. There's a definite first sibling, second sibling, third sibling, and that's always preserved.
Yes.
One. And the other thing is that in tree, you can have, you don't think of them as things with names. You think of them as things that can have a data in them. And so it's natural to have multiple places that have the same data.
Right, as opposed
to graph, you're accomplishing this by having under here, you have vertices. Like I see two F's here, but really you have two vertices with some names I don't know, and you're using a vertex label to make it show as an F.
Right.
But
whereas tree, it's like there's an F there.
But my question is, if we take this example here, if we just superimposed, say, 4 additional directed edges, perhaps in a different color, that had two edges between plus and F, and then one edge between F and 2, and another edge between F and 3.
It's not enough. It's not enough, I think. For the point that the point that Ian is making is, you need more information. You need, in this particular case, plus happens to be commutative.
So it's like you're using vertex labels to have sort of like a payload at each node, like tree does, and you're tagging the edges with part numbers so that you have ordering, like tree does.
Right.
That's my point. Is like graph, you're accomplishing with vertex labels and edge labels what the graph data structure doesn't actually store.
No, I completely agree.
That's all.
Right.
That's all the my observations.
Yeah, I think we're in agreement there. The only point that I'm making is that the same issue you have with pure edges, essentially assuming, for instance, in this case, that plus is commutative, is the same as the issue you have with representing it as a pure tree. And Ian, as you say, the way you get around that in both cases is by having additional information tagged onto the edges that tells you things about ordering and
right.
part
It just so happens that a tree, by its way,
right, but a tree is just a nested thing.
A tree just implicitly has that information, whereas a graph does not.
There's just explicitly a data in the expression at that location, and then there's explicitly a list of trees in the expression at that location.
Okay, so what we're learning here is that, in a sense, there is a I don't know what it is called. I mean, that you could imagine a data structure that is a combination of a tree and a graph, where, well, I guess it's like ports in graphs. Maybe Roger has something to say about this. I mean, that this is like numbered ports in a graph, is it not? I mean, a tree can be thought of as saying every node has a collection of numbered ports coming out of it, as opposed to a graph where where it's just a set of edges coming out, rather than an ordered list of edges coming out. Any comments? Does Roger have any thoughts on that? Anybody else?
Yeah, that ordering, every position. I mean, you could just use the pure tree is just a bunch of positions. It's a bag of positions.
Yeah.
And everything else is in addition. But the positions is the only thing that's needed.
No, I know, but the question is, from a graph, what is the combination data structure that is both has the features of a tree and the features of a graph? And I'm claiming it's a graph with numbered ports.
It depends. I mean, you defined a particular type of graph, a particular type of tree. That tree, that's an ordered tree.
What other kind of tree is there?
A tree is one where every node has a single ancestor.
Right. This is the thing that slightly confused me, right? Is that in a sense, the tree for +1, 2 is isomorphic to the tree +2, 1. As a pure tree. They're only distinct if they're ordered trees.
Yeah, I'm drawing a distinction between the Wolfram language tree and a tree graph.
Right,
Yeah.
right, exactly.
Yeah. And the things that you need for tree graphs are essentially payloads at the vertices, which you can already do with vertex label or just any annotation you want, vertex weight, whatever. And then you want ordering of the children.
Okay, look, I think we've defined here, what it is we need. That is, we're trying to have something which is both a representation of the structural tree and a representation of the evaluation process. And we've got different angles on getting to this. I think the one thing, so there's three kinds of, oh my gosh, there's so many different kinds of edges and so on here.
I think all the complication is because you're going to overlay them. As an animation, I don't think it is that complicated.
Interesting claim, Roger.
No, because you're trying to basically trying to show like
an evaluation graph.
Yeah, you're trying to show the dynamics in a static way.
Yes, I mean, we can try it, but I don't think it is. I mean, imagine our evaluator and imagine that you see an expression, and as an animation, and we could do this with trace actually, as an animation, you see different pieces of, if you want to unshare, Jonathan, I could.
Of course. Yeah.
But also you had that in some other thing I saw, like the nodes could be expressions, or trees. But they're not here. In all the things that we've seen today, they're sort of splattered out into pieces.
That's correct. That's correct. That's right. Because as soon as in order to understand evaluation or recursion through an expression, you have to go below the whole expression level. But okay, so another thing we could try to do is an animation of evaluation, e.g. using trace. Right, and so what we would see there is presumably we would see an expression and we would see things changing, flashing, that we'd see them changing. I don't know how we arranged to not have the thing jump around because of the changing, let's say we're doing full form, okay? We do animation evaluation, e.g. in full form. Is that what you have in mind, Roger?
Yeah, I mean.
Or in tree form.
Yeah, tree form.
Okay. I think it would be interesting to make that animation. I think it will be quite hard to understand, but we can certainly make that animation. I think it's a good idea. Now, I mean, like Fibonacci. Go ahead.
Can we go?
It's kind of like stepping through an evaluation. You can see things expanding out, contracting, this and that.
Well, you're right, but there are many different reference frames in which you can do that, and that's sort of an interesting thing to realize. In, for example, Fibonacci, there's depth first, evaluation. There's breadth first evaluation. You will see different things happening. Like in depth first evaluation, you'll always see just one piece of the tree lighting up at any given time. Whereas in breadth first, you might see multiple pieces. Well, actually, not breadth first. That would be generational evolution in a physics project terminology. Sorry, Jose, please.
I was going to suggest that after this discussion, we go back to the original tree of the trace with the trace original, and we try to read it again at the very top of your notebook. Yes, this one.
That one there.
This one you have, the larger one. This one, for example. Yes. So this with trace original true. Do you have one? Yes, the next one.
The next one, yeah.
The next one, yeah. So let's try to read this. So we start with f of 3. And so we will say we have to evaluate the head f, the argument 3. They don't do anything, so we have f of 3 again. So I'm reading horizontally. Now we have the rule that converts f of 3 into f of 3.
Which you can do when they're ordered trees.
Yes, exactly. So this is what we are trying to do, to distinguish the vertical direction from the horizontal direction. So I'm trying to read the order in which this is happening. So we say f of 3 is converted into f of 3 minus 1 plus f of 3 minus 2. Now,
and what Jonathan was showing was a nice representation of that step, right?
Right. So now we say we have an expression of head plus the first argument is f of 3 minus 1. But wait, we can evaluate f of 3 minus 1. So we go down. So we have f, and its argument is 3 minus 1. We can evaluate 3 minus 1, which is an expression of head plus 3 and minus 1. They don't do anything, so we get back 3 minus 1. And again, the internal rule evaluates that to 2. We go up, we have f of 2. And then f of 2 evaluates into f of 2 minus 1 plus f of 2 minus 2.
Yes,
which is an expression.
Okay, I admit I'm warming to this picture, although it would help me a lot to have some edges that join, there's an evaluation edge here.
Exactly. The horizon, there are several things in the horizontal steps. And I think that's the confusing point.
Well, maybe we should put those in. Maybe we should just have a representation of this in which we annotate the horizontal steps here. I mean, I think that that will be useful. Maybe we could do that, make that picture. And then it could be the case. Well, do you claim that contains? Okay,
my claim is that trace with trace original true contains everything. It's just hard to read.
I understand. So let's try and annotate this by changing edges and by adding some extra annotational edges. Okay, so let's take this case here. Okay, so this case here, these are recursion elements, right? These are the evaluator is going to this, to this.
Can you open the plot that Jonathan was showing side by side with this?
If Jonathan sends it to me, because it was on his screen.
Oh, sure. Yep. Give me 1 sec.
I should wrap this meeting up, unfortunately, but we're making progress here, guys. It's complicated. This is 40 years later, we're unbundling evaluation and expression structure. Are you sending this by mail or some other way?
I'm just about to email it to you.
You mean you're going to have to buy it separately?
Huh. No, we're going to be able. No, but the point is, Roger, that you're going to be able to run the evaluator multiple times on different on different threads and things. If we can understand how to do this, we can. That helps in saying I'm going to get 4 evaluators all at the same time.
Right.
Okay. All right. F of 4. Is this helping?
So these yellow events are what's missing between all of the siblings in the trace tree.
Okay. Let's make a picture.
Because you don't see what rule is being applied and how.
Yeah, I understand. And this question of where the rule comes from is yet a different level, which we also have to deal with. And that's what Nick's token event graph is showing, is where the rule comes from. But that may be another level of, complexity beyond this, where we assume for now that every rule is just, ab initio down code from the, already there type thing. All right, I do believe we're making progress. We had a couple of comments here from Richard. Let's see. Yeah, commenting on the use of non-deterministic rewriting. Yes, I agree. Okay, this is Richard commenting on someone's work introducing correspondence in program optimization and proof-to-proof transformation. Yes, that, in a sense, and maybe Roger can speak to this. In even from the 90s and 80s, all these things for doing parallelism and, optimizing loops and unrolling them and doing this, that, and the other. People had lots of program-to-program transformations, and which I guess in the modern view of proofs and programs being the same thing, which they obviously are, those techniques presumably read on proofs as well as they read on programs. Is that a fair, is that a useful comment, or is that, anybody want to comment on that? In other words, the techniques that people have for program transformation should also be proof transformation techniques and vice versa. Right.
That's correct. Yes. They're not, they haven't been necessarily packaged that way, but yes.
But so I would be curious to answer. I know Jonathan has been thinking about proof-to-proof transformations. Does anybody have any idea whether the traditional, I don't know what the good optimizations are. I don't know, various kinds of loop optimizations and so on in traditional.
Yeah. The families. So loop is one that I happen to know more about. So you can think of nested loops pretty much like nested sums or something like that. Mm-hmm. And it turns out that a lot of these transformations are things that people learn and give names to, like loop unrolling or loop reversals or loop transpositions. These have names in high performance programming, but they're all sort of special case. All of those happen to be unimodular transformations, like a change of variables, basically.
So like for example, loop transposition, I would imagine if you've got variables I and j, and j doesn't depend on the j loop, doesn't depend on I, but you keep on reevaluating the j loop over and over again. That would be an example of something.
Yeah, it would be an example. Sometimes you want to do transposition of loops to get a better stride for memory access, because that's such a crucial thing to get decent performance. So okay, so you access things that are nearby each other in memory.
So I'm curious, in proof optimization, is there any analog of loop transformations? Wait a minute. Nick has sent something through here. Should I run this?
Yeah, that looks fun.
My God, what the heck is this? Okay, f of 3 makes use of, why does it use that rule so many times?
Well, it uses it at each step because it can.
Okay, but f of 3 fundamentally using that rule is transformed to f of 1 plus f of 2. And f of 2, what is that? Is that a different kind of edge? That is kind of a subcase edge.
Wouldn't it have to use that rule again? The general rule, the Fibonacci rule up there?
Well, it will on f of 2. It's going to
that's just applying that other rule, the head of args.
Yeah.
Goes to list head args.
Oh, there it goes.
Oh,
yeah.
I see what's happening. I see. Head of args goes to list head args. I see. So that's basically a representation, sort of formal representation of the sequentiality of the evaluator.
Can you add this additional option? It will make things a little bit easier.
Also notice you can miss the base cases
Yeah, hold
depending
on.
on how you do the rewrite.
Where do I put that option?
For the token event graph.
Something is wrong with multi-clicking. I'm going crazy here. I rely on multi-clicking. Okay. F of 3 uses that rule to make f of 1 plus f of 2. Then it uses this rule to shatter that into f of 2, and that rule shatters it into f of 2 and f of 1. Right?
And plus.
Oh, yeah. There's plus down there, hanging out. Okay. Now, and that rule is also used on f of 3 to shatter that into 3 and an f, which doesn't do anything. And then here, okay. Well, so this is what we're looking for. I mean, this is, but it's interesting that you have, so in a sense, what we probably should be doing and what would make this clear is if we had two kinds of events, two colors of events. One is the rule application event, and the other is essentially the meta rule of the evaluator. That is, go head followed by args. Would that be, how does it reassemble? Given the head of args, how does it reassemble that? Or does it not need to for some reason?
This isn't representing the evaluation, though, right? This is like applying all possible rewrites.
You mean, is there an answer here?
Like, this is not like the trace.
Well, your claim is there is
Trace
no
is
answer.
like the single version of history or whatever.
Is this a multi-history thing?
Well, look at, like, you can get this down to these cases where you have f of -1.
That's true.
The one way of
That's true.
rewriting it, you end up in the base cases, but a different way you don't.
Right. Do I have the nerve to do this? Okay, so is the answer ever showing up here? What is f of 4 anyway? 1, 1, 2, 3, 5, 2, 3. Shoot, I can't see if I 1, 1. Am I going crazy? 2, 3. Really, I have to get 5. F of 6. The first place where I would see an unexpected number is f of 6. Is that true? Where I actually see a number that is a combination of multiple things. And this is probably going to get totally crazy. Not so crazy. Okay, is there an 8 anywhere in this picture? Because that would be a signal of evaluation actually having happened. I believe there is no 8 here. I believe that's because there's no additional rule here that goes from the shattered subparts of the expression to the, there needs to be another rule, I think, that, what the heck does it do?
You have to have a rule that reassembles the expression. It would be like, given some head and args, and a separate head and arg somewhere floating around, not evaluated already, so that you can use them in order to reassemble it. Something like that. It's more complicated.
Right. I think that's right. All right, we better wrap up for now. We are making great progress, guys. I mean, and what's also exciting is that a lot of these graphs, will have a single way version, and then we will immediately be able to make the jump to multi-way. And then we can start talking about traversal orders and, what count, because traversal order is ultimately going to, something like Fibonacci, we have confluence and we're going to get the same answer independent of traversal order. But in many cases, we won't. And particularly when the computations are infinite, it's going to be extremely non-trivial what the traversal orders end up being. Well, I'm excited. I don't know. I hope other people are finding this
I mean,
okay.
people are still working on Gaussian elimination. There's like a whole industry working on Gaussian elimination in its multiple ways in which it can be computed.
Which are essentially evaluation orders.
Yeah.
Yeah. Well, okay, so I'd love to know, Roger, if you have a pointer to that literature. One thing that we're trying to do here, which Ian has done a version of, is the taxonomy of tree traversal orders. Right? And so if there is a taxonomy of what amount to traversal orders in the Gaussian elimination literature, that would be interesting to see.
Well, they're usually called left-looking, right-looking, up-looking, etc. Frontal, multifrontal, supernodal.
Okay. Great, let's look these up. Those sound like leftmost, innermost, etc.
Yeah, they're all,
etc.
the whole literature is graph-based when you get to it.
No, but I understand, but I mean...
This is where a substantial part of graph theory got developed.
But there are names for these things in, in function evaluation, in recursive evaluation, like leftmost, innermost. And what you're saying, which is interesting, is that there's a correspondence of that in these numerical analysis schemes.
Mm-hmm.
Cool. Well, ultimately, everything's already been invented many times. The only question is whether people understand what it all means. And that's, yeah. I mean, that would be interesting, Roger. Would we be able to use that if we had a parameterization? Would we be able to actually use that in Gaussian elimination? I mean,
I think what people are doing is that they're trying to adapt to different hardware situations with memory hierarchies and accelerators and networking. So what's the cost? How much data are you moving? What's the cost of moving data?
Right.
And you kind of want to, like, for instance, in many cases, you want to be communication avoiding.
See, I bet there's an analog of that in physics. I bet there's a way of, or alternatively, well, I mean, that's a question for proofs, for example. Okay, so here's
for instance, in some cases, there are known lower bounds, and sometimes there is no algorithm yet found that achieves the lower bound. Sometimes there is one, but it's too asymptotically too complex. It doesn't actually.
Well, I would imagine in automated theorem proving, there are issues like, you want to minimize the amount of memory you need to store the intermediate expressions, for example. That would be an example of an optimization there. Analogous.
But there's for these things, when you want to find the best in that sense, I mean, the assumptions keep changing. That's what I'm saying. Like, our hardware today is a little bit different than it was 30 years ago. Because of the gap in speeds, like for compute versus communication. And so you have to change. But people often can. So the question is, are optimal algorithms even known? This is like fundamental pieces of our compute infrastructure.
Sure.
Like linear algebras, like nothing is pretty much as fundamental. Then we still don't have optimal algorithms.
Right.
And there's a whole industry kind of working on it.
Right. All right. Lots of interesting stuff. We really need to wrap this up for now, and to be continued.